Welcome to Science Matters, the holiday edition. I'm Lawrence Krauss. Today I want to talk about three different topics, and the first one I want to talk about actually harkens back to things I've talked about before. This seems to be the year of the black hole. And in the last month, there's been new developments related to black holes that I want to talk about. In particular, the discovery of black holes in a gap where there has never been black holes been seen. And the gap is kind of important. So I want to step back a little bit before I talk about how these different observations have all coincidentally been made in the last month, or at least reported in the last month. Black holes are fascinating. The key question is, do they exist in the universe? And that's been around since as long as people have been thinking about black holes. In particular, how can they form? The first person that really discussed how a real astrophysical black hole might form, although he wasn't talking about black holes at the time, was Subramanyam Chandrasekar, who eventually won the Nobel Prize for a calculation he performed when he was still a student. He was from India, and he was accepted for a fellowship at Cambridge. And in 1930, while he was still a student, on the boat to Cambridge, he did a calculation of trying to understand how stars would be stable, what the physical processes inside of stars would be like if you combined relativity and quantum mechanics. And quantum mechanics was a relatively new field in 1930. He combined them together and discovered something remarkable. That if the core of a star, which is burning its nuclear fuel, has a mass bigger than about 1.4 times the mass of the sun, then when you included relativity, the pressure generated by nuclear reactions would not be enough to hold that star together, and the star would start to collapse. There's no physical process that would keep atoms from having enough pressure, keep them having enough pressure to hold a star up. Just like this table has enough pressure to stop my hand from going through it, in a star, once the mass of this core is big enough, the gravitational force is strong enough that no process of nuclear burning that affects atoms could keep the atoms stable against collapse, and the star would start to collapse. It was a controversial result when he developed it, and in fact had to fight established astronomers like Sir Arthur Stanley Eddington for some time. But eventually, of course, it was proven to be correct. We now call that limit the Chandrasekar bound, that a core of a star larger than that amount will collapse. So that result was known. But the question is, what would it collapse into? And in 1939, Robert Oppenheimer, who was later on the director of the Los Alamos project, the Manhattan Project at Los Alamos, that developed the first atomic bomb, the nuclear physicist, began to think about what processes would stop that collapse and how you might form a stable object. And as the star is collapsing, eventually the atoms, which are mostly empty space, will get compressed and compressed and compressed till basically the nuclei of atoms, which are the very dense cores of atoms, much smaller than the size of atoms, will all be touching. And you'll form one giant atomic nucleus that I've discussed before, basically what we now call a neutron star. When that happens, nuclear forces will take over and produce new forms of pressure, and the collapse will stop, and that will generally produces a shock wave that kicks out the rest of the star, creating a supernova, which carries with it all the elements that have been produced by the star over the years, spews them into the cosmos, eventually to be captured by a nascent star like our sun, and all those elements like the carbon, nitrogen, oxygen, iron, all that stuff is what later on formed us and everything you can see in the studio. Great. But what Oppenheimer discovered was that at the time, based on the nuclear physics he knew, for bigger than about 3/4 times the mass of the sun, if you have a neutron star that's bigger than about that, he claimed that then even nuclear forces weren't enough to stop further collapse. And then in a subsequent paper in 1939 with another colleague, he basically showed that nothing would stop the collapse into what we'd now call a black hole, that no force could stop the object from eventually collapsing to a density where light couldn't even escape. Again, that was controversial at the time. And the nuclear physics that he applied was very preliminary because we didn't know a lot of nuclear physics then. Over time, those calculations improved, and the limit was now something like about between 2 and 3 times the mass of the sun. If you have an object that would form a neutron star that's more than 2 to 3 times the mass of the sun, nothing can stop it from collapsing into a black hole. So if we look out in the cosmos, we should see neutron stars up to around somewhere between 2 to 3 times the mass of the sun. And above that, we should see black holes if there were stars that collapsed that were larger, that had cores that were larger than that. So that sets the stage. The problem is we've seen neutron stars, and the most massive neutron star we've measured directly has been measured to have a mass of 2.14 times the mass of the Sun. The upper limit, based on the physics we think we know, is somewhere around 2.5 to 2.8 times the mass of the Sun. We think, based on the physics we know, there should be no neutron stars larger than that in mass. But any mass larger than that should be a black hole. The problem is, by many techniques, some of which I've discussed in other episodes, we've inferred the existence of black holes out in the cosmos by looking at, for example, objects that when a black hole captures material from a star, it'll emit X-rays, so we look at X-ray emitting objects. And many inferred black holes exist in the universe, but those inferred black holes all have a mass bigger than 5 times the mass of the Sun. So there's this gap that's been called a mass gap between 2.5 times the mass of the Sun and 5 times the mass of the Sun. And the point is, we haven't seen any black holes in that region, nor have we seen any neutron stars. What's the problem? We'd like to see what's in there to know what the dividing line is between neutron stars and black holes, because that's important for understanding a lot about the universe, as I'll get to. But in the past month or so, 2 independent groups looking at very different things claim to potentially suddenly see objects in that long missing mass gap. And the first one I want to talk about, and that's what this image is here about, it comes from, once again, another topic that's been very relevant lately, which is the observation of gravitational waves. Gravitational wave observations by LIGO and Virgo and other gravitational wave observatories have now detected over 21 events of black holes circling each other and eventually colliding. The first one, of course, was an astounding discovery, which later led to a Nobel Prize. When 2 black holes basically merge into one black hole, that incredibly intense event produces gravitational waves, which has been observed by LIGO and Virgo observatories. We've also seen 3 events of 2 neutron stars colliding and merging. And in fact, one of those 2 neutron star events, when the neutron stars merged, formed an object that was about 2.8 times the mass of the Sun. Is that object that was then formed a black hole or neutron star? We don't know. It's right at the boundary where it could be either. But recently, and it's kind of interesting for those who want to follow this in real time, you can actually go to the LIGO Observatory and get an app which will wake you up in the middle of the night, or just as it does the experimentalists, whenever there's a potential observation. And I think on September 24th, the observers at LIGO were woken up by such a ping from their apps, and it was a gravitational wave event, and it looked like it was an event from objects of mass 3.3 times the mass of the Sun. 3.3 times the mass of the Sun should, if we're right, be clearly a black hole. But if that's the case, it would be the first black hole that's ever been discovered in this mass gap. And we know that black holes exist in that region. If there isn't, then if that gap is truly empty, it'll tell us something about the nature of stars that collapse to form black holes, that there aren't stars big enough in the early universe to do that. So that's a preliminary observation, and the data hasn't been fully run yet. But the reason, if that were all that there was, I wouldn't bring this up in this episode. But what's interesting is, independently, by a very different route, another set of observations were claimed. And if we go to the next image, it was by looking at stars. A group out of Ohio State looked at 100,000 stars and tried to look for potential black holes, small stellar mass black holes. How did they do that? Well, the first thing they looked at, as we've talked about before, one way to discover planets around stars is to look for the stars to wobble back and forth. As the planets go around them, the stars wobble back and forth in response to the gravity of the planets. Well, of course, a black hole is massive and its gravitational force is fairly large of its closest star, so the star should wobble a lot. So what the observers did was look at this sample of 100,000 stars and look for stars that wobbled a tremendous amount. The way you can see wobbling is by seeing the light from the star redshift or blue shift. As the star is moving towards you, the light gets bluer. As the star is moving away from you, it looks redder. And if it's moving very fast, it looks a lot redder or a lot bluer. If it's moving slower, it looks a less redder and less blue. So they tried to isolate those stars that had incredibly fast motion back and forth, because that would mean they have a companion next to them that's very massive and potentially very close. And they isolated some of those. And then one particular star they looked at, and it has a long name, and I'm not an English name, but a name with lots of letters and numbers that isn't worth remembering. One particular massive giant star they saw wobbling incredibly, but they also saw the brightness going up and down. And they inferred, by studying that indeed they were able to measure and estimate the mass of this object and realized that it was a small enough object that as it came in front of the star, it was darkening the star, and going behind it wouldn't, and so that was causing the star brightness to go back and forth. And they inferred that they have seen a black hole of mass, guess what? 3.3 solar masses. Now, they can't be sure it's a black hole, except that they're not observing anything from that object except what it's doing to the star, and it's over 3 times the mass of the sun. So if it was a regular star, it would be visible. And if it's a neutron star, maybe there'd be some signals. And so they don't see any signals except what it's doing to the star, which is why they infer it potentially to be a black hole of mass 3.3 solar masses. Independently, these two sets of observations are suddenly seeing something that could be a black hole around 3 solar masses, which may mean that this mass gap is really populated, and by a new set of observational techniques, we could begin to understand those kind of black holes in the universe. The reason that's interesting for understanding black holes is that there could be millions or billions of them, because there are many stars that should be producing black holes in that range. And if they're out there, these new techniques may allow us to detect them. But more interestingly, from a fundamental physics point of view, we don't know the boundary between when an object will stop collapsing due to nuclear forces and form a neutron star, or when it'll keep collapsing to form a black hole. We know theoretically the number, but of course it's important to test these things empirically, because a number of things have been proposed that maybe the state of matter that collapses to form what we think is a neutron star might not be just neutrons. It could involve exotic states of matter, so-called strange stars, where the quarks that make up neutrons suddenly become liberated, and we form these really exotic forms of matter. If that's the case, then the equation of state, as we call it, of that system will be different, and the maximum mass of an object that won't collapse will be larger or smaller. So if we can find that boundary, it will allow us to test the nuclear physics that governs incredibly intense nuclear matter. And that's relevant because it'll tell us what types of supernovas can happen. Because remember, a supernova, an exploding star, only happens when you form a neutron star that stops the collapse, and that shock wave goes out. So if we knew the maximum mass of neutron stars, we'd know the kind of stars that could produce stellar explosions that might populate the cosmos, and we'd once again be able to have a better understanding of how the current universe got populated by elements that make you and I up. So these new observations may not just fill the mass gap for black holes, but tell us something, once again, about our own origins. And I found the fact that these two things came out in the same month to be worthy of mentioning. So that's the first topic I want to talk about. The second one is much closer to home and involves something that you may have heard about, something called quantum supremacy. It's been talked a lot about in the news lately. And if we go to the first slide here, this is a chip that was developed by Google. And it was developed by Google to try and, for the first time in human history, have a computer that exhibits quantum supremacy. What's quantum supremacy? Well, I've talked to you about the fact that quantum computers based on quantum mechanics may eventually be able to do calculations that classical computers can't do. Now, when I say that, that's not exactly correct, because a classical computer can do any calculation in principle. The question is, in practice, how long will it take? And John Preskill, an old colleague of mine when we were both together at Harvard, and I've written papers with him, has now become a leader in the area of quantum computing and quantum information theory. He proposed, I think in 2012, the idea of quantum supremacy, and that would be when the first time we have a quantum computer that can do a calculation that no classical computer could do in, say, in any practical amount of time, or maybe the history of the universe. You pick the number. Basically, from a practical perspective, a quantum computer could do in a finite time something that no classical computer could do in 10,000 years or 100,000 years or a million years or the lifetime of the universe. It's a threshold that tells us when quantum computers have reached a certain stage when potentially they may allow us to do things we could never do before. Quantum computers were first discussed probably by Richard Feynman in the 1980s with the idea that one can use the unique properties of quantum mechanics to allow us to do certain calculations we might not practically be able to do otherwise. And I've explained to you why, but I'll remind you again. A normal computer operates with bits, ones and zeros, and manipulates those logical bits using known operations to perform any calculation. The interesting thing about a quantum system, however, take an electron, which has its spinning around one axis in one direction or another direction. We call one of these a 1 and one of these a 0. Classically, it would be spinning one way or spinning another way. But quantum mechanically, as I've described to you, that's not the way the world works. An electron can be in a superposition of those states, where, namely, before you measure it, it's spinning both ways. It's spinning up and it's spinning down at the same time, as crazy as that may be. It acts like it's doing both, and when you measure it, you may find a 50% probability that it's spinning around this way, or a 50% probability that it's spinning around the other way. But before you make the measurement, you can't say it's in one state or the other. It's in what we call a superposition of states. But if that means if you have an electron like that, you can form what's called a qubit, not a bit. Namely, something which is in a 1 and a 0 at the same time. It's in both. And if it's in both states at the same time, in principle, you can basically be doing two independent calculations if you manipulate that at the same time, as long as you don't measure the electron. During internal stages, you could perform calculations, and at the end, you come up with a measurement that is the result of your calculation. But in the intermediate stages, you're basically performing many calculations at the same time. That's the power, in principle, of quantum computers. Now, Google created this chip, which contains basically 54, although only in this experiment only 53 were usable, 53 independent little circuit loops. Okay, but then if you cool this whole thing down to about 1/10 of a degree above absolute zero, these little circuits become superconducting. And when they're superconducting, what the strange phase of superconductivity, where currents can flow forever without any resistance, is a property of quantum mechanics. What happens is that entire circuit loop becomes a single quantum mechanical system. And so when they cool that whole thing down to a little bit above absolute zero, each of those loops, if you wish, becomes a quantum mechanical object, behaving purely quantum mechanically. And you can find that those systems can be set in, say, two states of excited states of currents flowing with different properties. Those two states can be ones or zeros. And when they're a quantum object, when you have a current loop that's a quantum object, it can exist in a superposition of those two different current states, a 1 or a 0. It suddenly becomes a qubit. So now you have, in principle, 53 qubits on this chip. Each of those 53 qubits would just be a single, if you wish, computer, but you can hook them up so that they can communicate with each other, and they can also be hooked up to the outside world so that you can manipulate them. And that's what this system was set up to. It turns out each qubit could interact with its nearest neighbors, and in that way, since one could interact with another, which then could interact with its nearest neighbor, all of these could be, as we're called, entangled. The whole system could be set up in different entangled quantum mechanical states. Okay, so now let's go to the next slide. So that's what the chip looks like. On the left-hand side, the chip has to be put in a dilution refrigerator and put in, basically all cooled to about 1/10 of a degree above absolute zero. And then, in principle, you have a quantum computer. Now we can go to the next slide. What's the power of this? Well, if you have one qubit, that qubit can be in two states, okay, 1 or 0, but of course it's in a superposition of states. So basically, if you want to think about it effectively, that qubit is in two states at the same time. If you want to think of the classical approximation of that, it's a superposition of both up and down. But if you have two qubits, that are interacting. Well, they can be now in not just 1 or 0, but 1, 1, 1, 0, 0, 1, or 0, 0. That's 4 states. So at a given time, this system is in 4 states at the same time. Okay? And if you measure it, you'll measure one of those, either 1, 1, 1, 0, 0, 1, or 0, 0. But before you make the measurement, it's in all those states. Well, if you have 3 qubits, you have 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, or 0, 0, 0. 8 states. So if you look at this, there's a pattern. With 1 qubit, you have 2 to the first power of states that are basically represented in that entangled state. That the state is a superposition of 2 different states. In 2 qubits, it's 2 to the 2 power, which is 4 states. In 3 qubits, it's 2 to the 3rd power, which is 8 states. If you have 53 qubits, then you see the power of this. You have simultaneously the system in 2 to the 53 states, which is about 10 to the 16th, which I think is something like a quadrillion number of states at the same time. And that means in principle, you could perform something like 10 to the 16th actions, calculations at the same time. Okay, for a classical computer, you'd have to be performing 10 to the 16th individual calculations, and depending upon the rate of a computer doing those, that could take a long time. So that would be wonderful if we had stable quantum computers that were operating and efficient and known to be quantum computers. We don't have that yet. But Google decided to set this thing up to do a very specific kind of calculation, which may not seem very relevant or interesting, but it exploits the power of quantum computers. It is a calculation that basically makes a system be a quantum system and asks you, can you calculate what state that quantum system was in? What the system was set up to do was basically have a random set of instructions, arbitrary, given to those 53 qubits, which would put them in some final state, which is a superposition of 2 to the 53 different states with a certain probability, okay? And then they'd measure it, and they'd get a set of 1s and 0s. And then they'd repeat that again and measure it and get a set of 1s and 0s, repeat it many times, and they'd find out what the probabilities were of getting 1s and 0s, and namely what the result of that calculation is. Great. It's a quantum mechanical system operating as a quantum mechanical system. It's not really it's effectively acting like a computer because the results are some number you care about. But it's basically just saying, let's put this quantum system in a certain state after a certain set of arbitrary number of instructions and then measure it. Now, if you wanted to know what the probability distribution of measuring 1, 0, 0, 0, 1, 0 or versus 1, 1, 0, 0, 0, 0, you'd have to do a calculation using quantum mechanics. The classical computer, to calculate all those probabilities, would have to calculate the probability that every one of the 10 to the 16th different configurations of that system existed. So it would have to perform calculations using the equations of quantum mechanics 10 to the 16th different times to know that probability distribution. And the Google people said it would take over 100,000 years for one of the world's biggest computers, which was in the picture on the right-hand side of that earlier picture. This happens to be an IBM system, and we'll get to that in a second. But if you had a room full of classical computers, they argued it would take 100,000 years to do it. Now, IBM, by the way, came back right after this was announced and said, no, it would only take us 2.5 days. But the point is, the Google people claimed that they did this with their chip and that it appeared to be acting quantum mechanically. It appeared to be behaving like a quantum computer. And in something like 100 or 200 seconds, they were able to get the answer, which is far faster than 100,000 years, far faster than 2.5 days. So the point is this interesting? And the answer is, in principle, yes, because what this demonstrates is, if it's true, is first of all that a quantum mechanical computer can do something that even the biggest computer in the world will take days, if not thousands of years to do. But it also suggests something else. It suggests we may be able to do a certain type of calculation in the near future or in the foreseeable future with quantum mechanical computers that would be interesting. But before we get there, we have to ask ourselves the question, how do we know it did the right thing? How do we know it was behaving like a quantum computer? Well, interestingly enough, the only way to know would be to look at the strings of ones and zeros it produced and compare it to the calculations from the classical computer to what quantum mechanics should give us to see if it was behaving appropriately. But of course, the problem is this calculation is beyond the capability of any large computer in any reasonable amount of time. So what they had to do was look at small subsystems and then with fewer qubits and see if those things were behaving as a classical computer might suggest they were, and then argue that the whole system would be behaving that way. But what's interesting about this is they argued it would take 100,000 years. IBM within a week said we could have an algorithm that would only take 2.5 days. The interesting thing is we don't know ultimately how fast a classical computer will be to calculate almost any calculation, because a smart programmer could improve the program. And by having quantum computers, we challenge classical computer programmers to develop better algorithms. So that's one thing. But secondly, it means ultimately that we can see if we can prove this behavior is behaving quantum mechanically, the computer is behaving quantum mechanically, we can test quantum mechanics, because the classical computer will tell us in principle what the quantum computer is doing, and if the quantum computer is doing something different, and you can confirm by many independent tests that it's behaving quantum mechanically, then it'll tell us that maybe our understanding of quantum mechanics is not what we thought it was. Now, I suspect that's not likely to happen. Finally, what's most interesting to me, and what Richard Feynman, who first proposed this, was thinking about, is that maybe we can perform calculations on quantum mechanical systems that we could never do before, because the computer is behaving quantum mechanically. So to understand behaviors of atoms or groups of atoms, to do those calculations, we just have the computer act like a group of atoms and then give us an answer, whereas a classical computer would take centuries or millennia to do that. So we may be able to use quantum computers to mimic quantum systems of interest. And that's what Richard Feynman once said. He said his interest in quantum computers was that they'd help him understand quantum mechanics in a way he couldn't do otherwise. And he won a Nobel Prize for his understanding of quantum mechanics. So this quantum supremacy, whether you like the idea of the name or not, heralds the point where quantum computers may one day allow us to perform calculations on quantum systems that we can't do otherwise. Otherwise, this kind of calculation was just really a proof of principle. It's not going to allow us to change the way we behave in any way, but it demonstrates that quantum computers can, in principle, allow us a new way to understand the universe, and I find that interesting. The last topic I want to talk about is a truly cosmic question related to the holidays, a question of profound importance that comes up every time this year, and it's illustrated in the following figure. How does Santa Claus get around the world in a given night to give presents to all the boys and girls in every country around the world? And people puzzle about this every year, and I thought I'd talk about it a little bit, because lots of different explanations are given, and I wanted to talk about each explanation. One of the explanations that's often I hear bandied about is somehow that Santa Claus is traveling near the speed of light, and as we all know, when you travel near the speed of light, strange things happen. For example, if I'm moving very fast compared to you, my clock is ticking slowly. So you could imagine if Santa Claus was moving very fast, what seems like a night for us could be like 100 years for him, and he would be able to deliver all the toys in an adequate amount of time. The problem is it doesn't work that way. First of all, the strange thing about relativity is, if I'm moving very fast compared to you, then my clock seems like it's ticking slowly compared to you. But if I look at your clock is ticking slowly compared to me. Things are equal. It works both ways, as strange as that might be. Now, that's produced a paradox, which undergraduate physics students have to deal with all the time, and it's called the twin paradox. If I have two twins, one's on Earth, and one goes out to a nearby star at near the speed of light, and you see that twin's clock ticking slowly compared to you, and then comes back towards you at near the speed of light, and their clock is ticking slowly, you may have aged 100 years or 20 years, and their clock will have maybe only aged a year. You would only have aged a year. How can that be if things are reciprocal in relativity? Well, the answer is that one twin is doing something very different than another. One twin is speeding up and slowing down, and therefore is behaving very differently than the other twin, which is just at rest. And therefore, the twin that's speeding up and slowing down knows that they're speeding up and slowing down, and the fact that their experiences are different than the twin that's standing still resolves that twin paradox. Things are only reciprocal when objects are in uniform motion with respect to one another, and the twin is certainly in uniform motion when he's going out, but when he stops and turns around and comes back, he has to decelerate and then accelerate, and it turns out it's during that time that the twin on Earth appears to age the extra 99 years for the twin who was doing the travel. That's the resolution of the twin paradox. All of the interesting stuff happens when you're speeding up and slowing down. Well, of course, Santa Claus has to speed up and slow down a lot to deliver the packages. And what's worse, Santa Claus in this case would be like the twin that's traveling to a nearby star. Santa Claus would be doing all the motion, and what that means is time dilation. The slowing of clocks works in the wrong direction for Santa Claus. Namely, for Santa Claus, what appears like one day might be 100 years for us. So relativity doesn't help Santa Claus at all. It makes Santa Claus's problem worse. If he's traveling near the speed of light, then one night for him is many years for us, and he hasn't delivered the presents on time. So relativity makes things worse, not better. What about the other explanations that are giving? One I've heard involves warp drive. Maybe Santa Claus has a warp drive like the USS Enterprise and can go faster than light. It turns out warp drive doesn't produce time dilation because, as I've discussed in one of my books, The Physics of Star Trek, well, the way warp drive works is you're standing still and you cause space behind you to expand and space in front of you to compress, and you appear to go from one place to another, but you haven't been moving at all during that time. It's space that's been doing all the work. And that's why time doesn't get dilated. Well, okay, that might solve the problem, except you're doing great damage to space. If you have a single spacecraft going from here to a nearby star with warp drive, all you have to do is compress the distance between you and the nearest star in 1 second and expand the distance between you and the Earth in 1 second and get from one place to another. But everything between you and the star gets squished, and everything between you and the Earth gets stretched. The problem with warp drive is it might be an in principle possible solution to Santa Claus's conundrum, but you basically kill everyone on Earth in the process by stretching and compressing the rest of the Earth. So that doesn't work either. The final argument that I've seen is actually says, well, Santa Claus isn't really traveling near the speed of light. Santa Claus just has to really travel at something like 11 million kilometers per hour, which is less than 1% of the speed of light. And if you work it out, someone worked out, and I took these numbers from a recent discussion. If Santa Claus went 510 million kilometers, that's 10,000 times around the globe, at 11 million kilometers per hour, be able to basically touch all the houses on Earth in a single night, including the fact that there's the international date line, so you have more than 24 hours, they would argue, to try and get things done. There's a problem with this, though. The problem is that what Santa Claus would be traveling on average is 3,000 kilometers per second. 3,000 kilometers per second. Still a small fraction of the speed of light, but pretty darn fast. Now, in order not to take any more time than necessary, after he zoomed down the chimney, he'd have to immediately accelerate once again to 3,000 kilometers per second at the end of maybe a second to get from one city to another. But when you go from rest to 3,000 kilometers per second, you have a problem. It's called G-forces. If I get in a Tesla nowadays and I use ludicrous drive, I get pushed back against my seat because I'm accelerating at maybe 1 G, which is basically going from 0 to 10 meters per second in 1 second. That's the same as the rate I would speed up if I jumped off a building towards the Earth. In 1 second, I'd start at 0, I'd be going 10 meters per second at the end of 1 second. That's called 1 G, because it's equal to the rate of acceleration due to gravity. Humans can experience maybe 3 Gs, most of us, and not black out. That's the number of Gs that the space shuttle astronauts experience. If you want to try and escape the Earth's atmosphere, the Apollo astronauts experienced maybe 10 Gs, and that's the maximum G-force you could experience, probably without blacking out for any length of time. But in fact, to accelerate to 3,000 kilometers per second, you'd experience about 100,000 Gs, and that would not be just enough to kill Santa Claus, but to destroy and squish his sleigh into nothing. So the bottom line is there's no physical way that Santa Claus can get around the world to deliver all of those presents. So how can we resolve this problem? The answer is quite simply, there's only one way, and that's magic. You can't use the laws of physics. It has to be magic. But of course, the holidays are a magical time, and I hope all of your holidays are magical, and you have a wonderful holiday season and a great new year, and I'll talk to you again then.